Hey everybody, this is Mr. Bortnick for AP Calculus AB. We are in Unit 5, Analytical Applications of Differentiation. Today's topic is topic 5.3, which is determining intervals on which a function is increasing or decreasing. Enjoy today's notes. All right, welcome to 5.3, where we're talking about increasing and decreasing intervals. Let's start off. It says find the critical points of the graph of f. Remember from our last lesson, 5.2, that we know that critical points are found from looking at the derivative, and they're places where the derivative of the function is either equal to 0 or it's undefined, aka or it does not exist in this case. So if we're going to find the critical points of the graph of f, we can see that there's a critical point here where the instantaneous rate of change, that slope is 0. We can see that there's another critical point here where that slope is 0. And we can see another critical point here where the slope is undefined because there is a cusp at that particular point. So when the slope of a function is positive, we say that that function is increasing. And when the slope of a function is negative, we say that that function is decreasing. So we notice that on this particular graph that in general, when thinking about a function either increasing or decreasing, it is extremely useful for us to mention that we read a graph like a book from left to right. From left to right. When you are looking at a graph and you're reading a graph, you look at the left side first, then you look at the right side. We notice that on this part from here to here, that function has a positive slope, that if I draw any little tangent lines on this, that they have positive slopes for this. And so if we're thinking about how we would define this particular function, we might notice that on this interval from here to here, that the slope is positive going all the way up until it hits this maximum that we've got up here. And then suddenly we see that the tangent lines have negative slopes. It is decreasing until it hits this minimum down here. And then we see it's got a positive slope up until it hits this critical point where there is a cusp, after which we see that the slopes are negative. So one thing to notice is that frequently these critical points are useful because not only do they identify possible maximums and minimums, but they also identify places where the function switches from increasing to decreasing, or they possibly switch from increasing to decreasing. So it's useful when we're trying to figure out where a function is increasing or decreasing to identify those critical values, those critical points, because it's going to help us figure out the intervals on which the function is increasing or decreasing. So let's use what we've got here on our graph. Let's represent this as a table. Frequently, in support of our work, we're going to be using tables to represent these intervals of increasing and decreasing by looking at the intervals themselves and the sign of the derivative there, the sign of f prime of x. Again, that's the sign of the slope of the tangent line at a given point on that interval. What we do is we're going to identify the x values. We see that critical value that we had was at x equals 3. This critical value was at 5, and this critical value here was at 6. So I'm going to leave some spaces between them. I'm going to put 3 and 5 and 6 as the x values where those critical values occurred. Between those, what we're going to do is we're going to represent the intervals, thinking about the domain of the function going all the way from negative infinity to infinity that is separated by these intervals. And so the first interval we're going to represent is all of the values that are less than 3. We can write that as the interval from negative infinity all the way up to 3. Then we can represent all of the x values between 3 and 5 by writing this interval from 3 to 5. Then all of the x values between 5 and 6 by writing 5 comma 6. And then all the great values bigger than 6 are going to be from 6 to infinity. Note that, again, that these are representing intervals of x values. These are not coordinates, right? I'm not talking about the point 3 comma 5. I'm not talking about y values at all here. We are just talking about the behavior of f prime of x on these given intervals. Now we saw at x equals 3 and at x equals 5 that the slopes of the slope of the tangent line was 0, which means that the derivative was 0 at both of those values. We also saw that there was a cusp at x equals 6, so we know that x equals 6 that the derivative does not exist. From there, we are going to look at the signs of f prime. Now we saw that when x was less than 3, that the derivative was positive. So I'm going to just put a plus sign there to represent that the derivative was positive. We saw that from x equals 3 to x equals 5, that the slope of the tangent line was negative. So I'm going to put a little minus there. We saw from 5 to 6 that the slope of the tangent line was positive. And then we saw after 6 that the slope was negative. So we're going to put a little minus sign there. So this is what we refer to as a sign chart. This is a sign chart. And we're going to be using these over the next couple of lessons to talk about, whether functions are increasing or decreasing, talking about later about maximums and minimums, and what information we can tell about functions from the sign charts of this. Again, I'm going to just sort of emphasize here, we know that this function is increasing on these two intervals because the derivative is positive, the slope of the function is positive, while it is decreasing on that interval and this interval here because the slope of the tangent line is negative on those intervals. Number 1, find the intervals on which the function f of x is equal to negative x squared minus 4x minus 1 is increasing and decreasing, and justify your answers. These steps are going to walk us through the process of this. So first, find the critical points. Again, critical points are places where the derivative is equal to 0 or it does not exist. And so we can see that this is a well-behaved function. There's no places or no x values where that would cause this to be undefined. So in that case, it can only equal 0. And actually, that's the original function, so we wouldn't even want to be looking at that. We want to be looking at f prime. So let's take that derivative first. So f prime of x is equal to negative 2x minus 4. Similarly, again, well-behaved. There's no x values that make this undefined. So let's find out what makes it equal to 0. So negative 2x minus 4 equals 0. So negative 2x is equal to positive 4. That means that x equals negative 2. This is the only critical point for this function. Now, in between the x values, the derivative must be positive or negative, right? It's gotta have some sort of sign. And so there's only one x value here, but around the x values, the values of the domain, the derivative has to be positive or negative. So we can use a sign chart to help keep track of the information. We're going to write the critical points of the derivative first. So I'm going to draw my lines here. Negative 2 is the x value that we found, so that's going to go on our critical value. And we know that at x equals negative 2, that the derivative is 0, right? That's how we found it, by taking the derivative and setting it equal to 0. So the derivative is 0 when x is equal to negative 2. What I want to then do is I want to identify the other parts of my domain. So I want all of the numbers that are less than 2, so going from negative infinity all the way up to negative 2. And then from all the numbers bigger than negative 2, so negative 2 all the way up to positive infinity. Right? Again, we're representing these using interval notation, which is not the same thing as coordinates, but that's super useful for us to notice. And all we're going to do now is we want to figure out the signs of f prime of x on both of these intervals. Now, because this is the only critical value, I can essentially pick any x value between negative infinity and negative 2 and find out what the sign of the derivative is. I'm saying that all of the x values less than negative 2 are going to have the same sign for f prime of x. And all of the values that are bigger than negative 2 are going to have the same sign for f prime of x. So what I'm going to do is I'm going to actually just pick a test point. So a test point on that interval. I'll do x equals negative 3 for that one, and here I'm going to do x equals 0. So negative 3 is between negative infinity and negative 2. X equals 0 is between negative 2 and infinity. And I'm going to just think about what would happen if I plugged it into the derivative function. So if I do that, f prime of negative 3 is equal to negative 2 times negative 3 minus 4. 6 minus 4 is equal to 2, and that is positive. So it's going to get that little plus sign there. Here, if I do f prime of 0, that's negative 2 times 0 minus 4, so that is negative 4, and that's clearly negative, so we're going to get that minus sign there. So what is this sign chart saying? It's saying that for all of the x values between negative infinity and negative 2, that the derivative is going to be positive, and all of the x values between negative 2 and infinity, the derivative is negative for that. So what is our answer statement, right? The original question here was, where is it increasing and decreasing, and to justify our answers. So our conclusion here is we know that f of x, the original function, is increasing. It is increasing on the interval from negative infinity to negative 2, since f prime of x is positive. We know that a function is increasing when the derivative, aka the slope of the tangent line, is positive. Similarly, f of x is decreasing on the interval from negative 2 to positive infinity, since on that interval the derivative is negative, so f prime of x is less than 0. And so our statement is the first part. The conclusion is bringing in the information about the derivative. If I'm going to make an argument about a function, whether it's increasing or decreasing, I need to be justifying using the derivative being either positive or negative. Again, the sign chart is a really nice way to help us organize that information, but on its own, it's not the justification. I can't just make a sign chart and say, okay, it's f of x is increasing and decreasing on these two intervals, and then just point at that. I need to be able to explain my reasoning as the justification. And so saying, hey, I know the derivative is positive, so this is essentially support work. It is not the justification by itself. Great, let's move on to number 2. Problem number 2 says to find the intervals on which the function f of x is equal to 1/3 x cubed minus x squared minus 15x plus 2 is increasing and decreasing, and justify your answers. So unlike number 1, they gave us sort of these like baby steps along the way. We're going to do these same baby steps, but they're not asking for A, B, C, and D. There's no parts to this. We're going to need to find the critical values first if we're going to complete our sign chart. So I want to find, again, critical points are going to be places where f prime of x is 0 or does not exist. So let's take the derivative of this. The derivative appears to be 1/3 times 3x squared, so that's just x squared minus 2x minus 15 if we do the power rule for that. And it can't be undefined, right? There's no denominator here. There's no radical function. So I'm really looking for places where this is equal to 0. So x squared minus 2x minus 15 equals 0. This is a quadratic. And so if we're going to find out where it's equal to 0, it would be best to factor it. And so if we think about our x method from earlier this year, we could factor this into x minus 5 times x plus 3. That's equal to 0. So our critical values are x equals 5 and x equals negative 3. Critical points. So that is useful for us. Now, the reason, again, why I'm using these critical points is it's going to help me separate my sign chart. So I want negative 3, I want some room, and then I want 5. And again, I want an interval below negative 3, I want an interval between negative 3 and 5, and one that is bigger than 5. We're again going to bring in interval notation to represent the intervals around these critical values. So less than negative 3 would be from negative infinity to negative 3. Between negative 3 and 5 would be like this. And then larger than 5 would be 5 to infinity, like that. Similar to our previous ones, I want to think about some test points. So I'll do x equals negative 4, I'll do x equals 0, and I'll do x equals 6. And all I'm going to do is I'm going to think about what would happen if I plug in these functions or these x values into our derivative. And I'll think about the factored form. If I do negative 4 minus 5, that's going to be negative 9. Negative 4 plus 1 is negative 1. So a negative times a negative is a positive. So the derivative is going to be positive for that. At x equals 0, we've got negative 5 times 3, so that's going to be a negative number. And then here we've got 6, so 6 minus 5 is 1, 6 plus 3 is 9, so positive times a positive is a positive. And so we've got the signs of our derivatives on each of these intervals. Of course, we know that the derivatives at negative 3 and 5 are 0, because that's how we found those, was by setting the derivative equal to 0 at those values. As a side note, I just want to mention, it's also really nice for you to be able to visualize these parent functions. We know that x squared minus 2x minus 15 is a quadratic, and the graph of that is a parabola. And so it's useful if we're thinking about curve sketching, right? Like, what is this going to look like? I know that if I were to graph this this function here, this one, that it would have an x-intercept of 5, an x-intercept at negative 3, and that the graph of it is going to be a parabola, right? It's going to be that U shape. Now, the only question I have is that U shape going opening upwards or downwards? And since our a value here is positive, I would expect the graph to look something like this, right? It's going to go through those points and go up. And so one shortcut way you can think about this, if you don't want to use actual test points, is if you know what the graph of the derivative is looking like. I notice that these outputs for the derivative are above when x is less than negative 3. I see that the outputs are below when x is between negative 3 and 5. And I see that the outputs are above 0, or positive when x is greater than 5. And so notice that corresponds, the positive to positive, with the signs of the derivative here. But if you are not a visual person who can recognize that curve sketching, using test points is a fine way to go about this process as well. Just requires you to actually plug them in and think about the signs for that derivative as well. So what is our conclusion, and what can we justify here? We can say that f of x, so our function we're talking about, has to be increasing on any interval where the derivative is positive. So it's on negative infinity to negative 3, and, so a union, 5 comma infinity. So the interval from negative infinity to negative 3 and 5 to infinity, here's a union saying both of these. It's the mathematical and our justification for that is because that is since f prime of x is positive, it's greater than 0. And whenever that derivative is positive, we know that function is increasing. Similarly, f of x is decreasing on the interval from negative 3 to 5, since f prime of x is negative. And so that means the slope of the tangent line is negative, so therefore that function is decreasing. All right, number 3, a super common problem on the AP exam. They give you f prime of x. You have a graph of f prime. We're trying to figure out, is f increasing or decreasing? Notice that this is not asking us about f prime. They're asking us, what do we know about the function f given its derivative? So I want to determine the intervals where f is increasing and decreasing based on the graph of f prime. We know that when f prime is positive, so when f prime is positive, it's increasing. And we know that when f prime of x is negative, it's decreasing. And so in this case, because this is already the derivative of f, I'm not looking at the slope of this. I'm actually looking at the outputs of the function. I notice that we have outputs that are above the x-axis that are positive when x is less than negative 3. I notice that I have outputs that are negative between negative 3 and 1, and then positive outputs between 1 and 3. Whoops. And then negative outputs again when x is greater than 3 here. So in terms of intervals, we would say here that this function, that f of x, so f of x is increasing on the interval from, looks like negative infinity all the way up to negative 3. So we're talking about really this part right here, right? That's above the x-axis. And the interval from 1 to 3, So the interval from 1 to 3, because that's above the x-axis. And we're going to say that since f prime of x is positive on those intervals, right? The output of that f prime function is positive. So therefore, f prime of x is positive there. We're going to also say then that f of x is decreasing, where the outputs of that function is below the x-axis. So really on these two intervals that we see right here. So what are those two intervals? I'll set up my little red lines. Looks like that's going to be between -3 and 1, and when x is greater than 3. So from 3 to infinity. And we know that it's decreasing since on those intervals f prime of x is negative. It's below the x-axis. So that is interesting because, again, we are able to find information about the f of x function even though they didn't give us anything about f of x. They only gave us its derivative. And I already know that it's increasing on some intervals. I know it's decreasing on some intervals just from looking at the derivative of that graph. Nice. Last piece for this is we're going to talk about the application of the rate of change. If you want to know if something is increasing or decreasing, you look at the sign of its rate of change, right? The rate of change is the derivative, right? The rate of change is the derivative. So those are sort of synonymous in this case. And the sign of a rate of change can tell you if the dependent variable is increasing or decreasing. So the dependent variable is generally in the numerator of these. So if we're talking about the dependent variable, that's going to be in the numerator of these rates of change. So if I know that the students per year is greater than 0, my conclusion for that is that the number of students is increasing, because the derivative, students per year, is greater than 0. If I have miles per hour is less than 0, the number of miles is decreasing, because that derivative is, or that rate is negative. Mastery checks per week is greater than 0, so the number of mastery checks since that rate is positive, it is increasing. And virus cases per month squared. So I'll emphasize we've got that squared on that unit. So it's the rate of change. So the rate of change, the rate of the virus cases per month, is decreasing because that derivative is negative. Last problem, number 4, the rate of change of fruit flies in Mr. Kelly's kitchen at time t days is modeled by r of t, flies per day. Show the number of flies is decreasing at time t equals 3. We want to find that the number of flies is decreasing. So if the number of flies is decreasing, we would expect to see the rate to be negative. And we have already the equation of the rate of change per day here. That is this equation that they gave us. So really here, I actually don't even need to take a derivative because this rate, or this r, is already the rate of change. And so I need to just show that that r of t is negative. So if I do r of 3, we can say that that's going to be 2 times 3 times cosine of 3 squared. I would throw that in my calculator since I don't know what cosine of 9 is. If it's in radian mode, you're going to get negative 5.467. Again, we round to 3 digits after the decimal place. And so because that rate is negative, the rate is negative, therefore the number of flies at t equals 3 days is decreasing, since r of 3 is less than 0. Great. That was our notes for 4.3 or, yep, 4.3. Nope, 5.3. We have got some practice for you to check out. As usual, the answers are posted. Come to class with any questions you've got, and good luck on your mastery check this week. Please reach out if you've got any questions, and I will see you around. Take care.